Hey guys, my name is Prasad and I welcome to you guys in my today's video. I hope you guys are staying safe and healthy. So in today's video, I'm going to talk about different graph representations, and I will discuss adjacency matrix, which is one of the graph representations in depth. So let's begin. There are different ways in which we can represent graphs. One way is adjacency matrix, another way is age list, there is another way is adjacency list, and a slight variant of adjacency list is adjacency map. So in today's video we will discuss about adjacency matrix, and in subsequent videos we will keep discussing other representations of graph. So while discussing adjacency matrix, first we will see what is adjacency matrix and how we can represent graph using adjacency matrix, and then we will talk about the space which it takes when we represent a graph using matrix, what kind of space, how much space it takes, and the third thing we can discuss is there are certain operations, right? So while performing those operations, what is the time complexity? What kind of time it takes to finish those operations? And finally, we will discuss in what is the situation when we go for adjacency matrix to represent a graph, when it is appropriate to use adjacency matrix as a graph representation, and what are the situations when we should not go with adjacency matrix to represent a graph. Adjacency matrix is nothing but a two-dimensional matrix or two-dimensional array. The rows and the columns are basically showing the vertices or nodes in that graph. So here I have a graph which has 4 nodes. So that's the reason I have taken a matrix of dimension 4 by 4. So it has 4 rows and 4 columns. Altogether there are 16 cells inside this two-dimensional array or matrix, and every cell represents an edge. So for an example, if vertex 1 and vertex 2, if they have an edge connecting both of them, both those vertices, then we will mark this cell as 1, or if they don't have any direct connection, then we will mark it as 0. So let us use this graph and try to represent this graph in this adjacency matrix. So we have an edge between vertex 0 and vertex 1. So this is vertex 0 and this is vertex 1. So we will mark it. We will mark it as 1. We have an edge from vertex 0 to vertex 3, so we will mark this cell as 1. There is another edge going out from vertex 3 to vertex 1, so let us mark this as 1. Another edge from vertex 3 to vertex 0, so mark this cell as 1. Let us go to vertex 2. So from vertex 2 there is only one outgoing edge to vertex 1. So from vertex 2 to vertex 1 we mark this as 1, and from 1 we have edge to 0, we have edge to 3, and we have edge to 2. And if you see this diagonal in this matrix, so basically it states that 0 to 0, 1 to 1, 2 to 2, and 3 to 3. So we will because essentially it is the same node, we will mark all these diagonally located cells as 0, because really there is no any edge exist. As I said, this is undirected graph. Hence, when we talk about this edge between vertex 0 and vertex 1, this edge, when we say this edge is going from vertex 0 to vertex 1, it is true other way around. So the same edge is going out from vertex 1 to vertex 0. And hence, what we have done here is we have marked 0 to 1, 0 and 1, this cell as 1, and 1 to 0, which is this cell, we have marked even that cell as 1. Hence, you will see a symmetry in this matrix. So, if you carefully look at this matrix, and if you see, if you take this diagonal as the middle edge, let me fix this line. If you take this diagonal as the middle boundary, then you can see that all the ones are symmetrically exist in these two parts of the matrix. This is one part of the matrix, and this is the another part of the matrix. So you see one exists here, one exists here, one exists here, one exists here. This one is symmetrical to this, and this one is symmetrical to this.